Hey everyone, and welcome. Today we're going to dive into a really cool manufacturing process that uses one of the most basic forces of nature, fire, to solve a problem you've almost definitely run into. Yeah, you know what I'm talking about, right? You get a new gadget, and a week later, the logo is already flaking off. Or you try to put a sticker on something plastic, and it just won't grip. It's super frustrating, and it happens all the time. So, what's actually going on here? Well, the root of the problem is something called low surface energy. Basically, the surface is just too slick on a molecular level for anything to hold on to. But the solution? This is where it gets wild. It's a precise, controlled flame. So in this explainer, we're going to break it all down. We'll start with why things don't stick, then see exactly how fire fixes that. We'll get into the tricky business of tuning the flame, look at the proof that it works, and finally see how it stacks up against other tech out there. All right. First up, let's get right to the heart of it. Why are some surfaces so darn hard to get anything to stick to in the first place? The best way to think about it is like a freshly waxed car. Water just beads up and rolls right off, right? That's because the wax has low surface energy. Well, a lot of plastics are kind of like that naturally. Their surfaces are chemically, lazy. They're smooth, they don't want to react with anything, and that gives glues and inks absolutely nothing to grab onto. And that brings us to the main event. How can a super carefully controlled flame take one of those slick surfaces and turn it into something that's ready to bond? It's not just about making it hot. It's this really clever two-part chemical trick. Okay, so let's be super clear here. We are not talking about taking a blowtorch to a piece of plastic. No. Flame surface treatment is a super precise engineering tool. It uses a very specific mix of gas and air to create a flame that doesn't just heat the surface. It fundamentally changes its chemistry. So here's how it works. It's kind of like a 1-2 punch. First, the heat is like this incredible power washer. It just vaporizes and burns off any microscopic gunk on the surface. But then, the real magic happens. There are these super reactive particles in the flame. They're called radicals, and they just bombard the surface. What they do is create thousands of new chemical hooks, these things called polar groups, and those hooks act like molecular Velcro, just waiting to grab onto whatever you put on next. But, and this is a big but, getting this right is incredibly difficult. You can't just aim a fire at something and hope for the best. It's all about tuning a whole bunch of different variables with just insane precision. It's a real high-stakes balancing act. And just look at this. Every single one of these factors is a trade-off. If you get the temperature or the exposure time just a tiny bit wrong, you could melt or weaken the whole part. Flames too close, you cause damage. Too far, it does nothing. Even the fuel-to-air ratio has to be absolutely perfect. Otherwise, you just get a sooty mess instead of a perfectly prepped surface. And this quote from some research by Poor Hosseini just shows how sensitive this all is. All they did was pre-process the fuel a bit, a technique called bireforming, and it completely changed the flame. It went from blue to yellow, got hotter, and kicked out 30% more heat. That one little tweak totally changes how the flame interacts with the material. This need for precision even extends to the byproducts. Check this out. Research from Jazieri and their team found that the sweet spot for treatment, right around 1500 degrees Celsius, is on a total razor's edge. It's the exact point where nasty nitrogen oxide emissions are at their highest, just as carbon monoxide hits its lowest point. So what does that really mean? It means the people running these machines have to find this tiny, tiny little window of operation where they get that perfect surface treatment while also making sure they're managing the environmental side of things. It is an incredibly precise science. So with all this complexity, how do we actually know it's working? Well, the proof, as they say, is in the pudding, or in this case, in the properties. The results are real things you can measure. And the change is, it's night and day. Before you do the treatment, a drop of water will just bead up on the surface. That shows you have a high contact angle, it's not very wettable. But after, that same drop of water spreads out totally flat. The surface energy is now way up, and its ability to stick to things is just massively improved. And look, this isn't just something you can see with your eyes. The science backs it up. 100%. This study by Lapana and Lopes confirms everything. Water contact angle plummets. Their chemical analysis proved that those crucial hook molecules were created, and physical tests showed that, the adhesion was way, way better. Scientists have this whole toolkit to double and triple check the results. They do the wettability tests with water droplets, they use these advanced chemical scanners to actually see the new molecular hooks, they check for any microscopic damage with powerful electron microscopes, and finally, they just use brute force. They try to pull the new layer off to prove the bond is stronger. Okay, so last up, where does flame treatment fit into the big picture? It's a powerful tool for sure, but it's not the only one. So let's see how it stacks up against the main competition.
The other big player in this space is something called plasma treatment. Now, they're both trying to do the same thing, but they go about it in different ways. Flame treatment, with its hot gas, is also for tough materials and really fast production lines. Plasma, on the other hand, uses charged ions and electrons. It's much better for delicate stuff that's sensitive to heat, or when you want to create a really specific texture on the surface.
So at the end of the day, there's no single best answer. The right choice is all about the material you're working with. A really tough, high-performance polymer is going to need a totally different approach than your average consumer plastic. It really is all about tailoring the tool to the specific job. So when you boil it all down, flame treatment is just a fantastic piece of technology. It takes the raw, chaotic power of fire and dials it in with incredible precision, all to solve one of the most basic challenges in manufacturing, making sure the stuff we build actually holds together. It really makes you think, doesn't it? If we can use a controlled flame to make slippery plastic sticky, what other weird, counterintuitive bits of physics are out there just waiting for us to discover? What else could completely change the materials that build our world? Thanks for joining me on this explainer.